Right now, artificial intelligence is resolving hyper-realistic images from raw digital static. These scenes are constructed in seconds, translating simple text prompts into coherent visual structures. At Treecapital AI, we are investigating the specific mechanical engine that drives this type of construction. To understand the logic, think about dropping red dye into a beaker of water. The laws of physics dictate that those particles will spread evenly until the system reaches equilibrium, clouding the water completely. That physical process is called diffusion. But now, imagine trying to reverse that process. How could you mathematically extract every microscopic particle of red dye and return the water to its original clear state? In the physical world, reversing entropy is impossible, but teaching a machine to reverse digital chaos, to pull a clear picture out of a sea of random noise, is the mathematical foundation of modern generative AI. The system learns this through a process called forward diffusion. It starts with a clear training image. If we look at just one single pixel, its color is represented by 3 specific values on an RGB plane. The goal here is to systematically destroy that original color. A mathematical sequence called a Markov chain adds random Gaussian noise to that pixel at each time step. The system samples numbers and adds them to the original RGB values, subtly shifting the pixel's color away from its starting point. Over thousands of time steps, this noise compounds. The shapes and edges in the original picture blur and degrade until the structure is gone, leaving a screen of unrecognizable TV static. This destruction is a requirement for the system. By reaching a state of pure mathematical variance, the AI creates a blank canvas. From this absolute static, any new image can be born. To create that new image, the model has to run the sequence backward. In reverse diffusion, the system starts with random static and attempts to backtrace the Gaussian noise, removing it step by step. Michelangelo famously noted that the statue already exists inside the block of stone, and the sculptor only needs to discover it. Reverse diffusion treats a block of digital static with the same philosophy. Our digital sculptor is a neural network called a U-net. When fed a block of static, the U-net does not guess what the final picture should be. It learns to predict the noise that was added at the previous time step. By subtracting that predicted noise, the model peels away the fog layer by layer. Eventually, the static clears enough to reveal physical features, like the outline of an arm or the edge of a landscape. The U-net is not painting a picture. It is running an algorithmic subtraction sequence that mathematically forces order back into the pixels. But if the U-net is strictly removing noise, how does it know which specific image to construct from the static? This requires text embeddings. The system takes human words, breaks them into tokens, and converts them into mathematical vectors. The semantic meaning of the language is mapped as coordinates alongside representations of images. Through self-attention guidance, these text vectors act as constraints. They force the U-net to focus on specific regions of the noise that correlate with the meaning of the prompt. As the model iterates, the final layers of static are removed under the guidance of those vectors, shifting the pixel values toward the requested image. This is a controlled mathematical translation. It takes the meaning of language and maps it into the coordinate logic of pixels. Reverse diffusion provides a framework for granular pixel control. This capability enables image-to-image editing and the prediction of sequential video frames. In marketing, this allows teams to bypass production bottlenecks and generate hyper-tailored visual assets in seconds. Clinicians are applying these models to medical imaging, stripping away artifacts from low-resolution scans to produce high-fidelity diagnostic tools. Molecular biologists use diffusion to model the 3-dimensional structures of complex molecules, mapping out pathways to discover new drug combinations. Because these models operate on the underlying patterns within visual data, the same logic used to generate a marketing asset can be repurposed to identify a molecular bond or a medical anomaly. Deploying these models at an enterprise level introduces a challenge: securing the underlying data. This requires the use of sovereign architectures like Anven AI. This graphic shows the architectural shift required for security. While legacy models use rented public APIs with data exfiltration risks, Anven provides a sovereign intelligence stack. This ensures total governance by keeping the weights and processing entirely on-premise. Looking at Anven 1.1's late fusion architecture, we see how the cross-attention module handles multimodal inputs. The image token acts as a gatekeeper, merging raw visual data with text queries before generating an output. allowing the system to reason about images without external API calls. This deployment pipeline shows how Anven optimizes these models through quantization. The system can scale from large server blocks down to embedded microchips on edge devices like smartphones without losing analytical power. Diffusion models teach computers to translate language into visual reality. They give enterprise systems a mathematical tool to find perfect order inside absolute chaos.